Okay, so I want to point out some simple basic cryptography here. And the first one, let me get rid of this cryptocurrency stuff. All right, the first thing is just binary games. If your students don't know binary, they have to learn it at some point. And I made some lessons here, which seem to be a fun way for them to do that. So if you haven't done this before, it might be good to look at and show your students. One thing I learned is you cannot teach binary all in one lesson in one night. Nobody will get it. The best thing to do is just do 5 minutes of it every week. And the next week, do another 5 minutes. That way they learn it and they don't get angry. Because the problem with math of all kinds is you really have to understand step one and you have to practice it until you've got it before you can do step two. And if you cover 8 steps in one night, nobody will get it. So the first night I just do nibbles. So nibbles are 4 bits. Now, normal numbers like 147, the 7 is the number of ones, the 4 is the number of tens, and the 1 is the number of 100s. It looks like this, and we're all used to that. In base 2, all you have is 0 and 1. So if you write 1, 1, that means 1, 2 plus 1, or 3. So it's like this. The number on the right is the number of ones. The next number is the number of twos. And the next number is the number of fours. So this is 5. It's a 4, no 2, and a 1. So if you count to 7, it looks like this. In base 2, 1 is 1, 1, 0 is 2, 1, 1 is 3, and on up to 1, 1, 1 is 7. And if you have 4 bits, you have 1s, 2s, 4s, and 8s. And there are a total of 16 possible nibbles, as you see here, from 0 up to 15. 1, 1, 1, 1 is 15. And 10, 10 is 10 because it's 8 and 2, and so on. And so after you review just a simple lesson like that, then you practice. This is an idea I got from the Khan Academy. You don't go on to the next lesson until you've really learned the previous one. So here, you have to do this. 10, 10 is 10. That's 1.
12, 13.
And that's 8 and 4 is 12, and 1 is 13, and so on. And when you get 10 in a row correct, then you get a flag. And so I got a series of binary lessons here like that. First nibbles, then bytes, then hexadecimal. And let me mute that one. All right. And then modular arithmetic. So these are the nibbles, bytes, and hexadecimal, I imagine, are probably pretty familiar. But modular arithmetic and the second one might not be. So let me talk about that. This stuff might be of interest. So modular arithmetic is essential for cryptography because if I have a bunch of letters and I encrypt them, and each letter is, say, 1 byte, I don't want it to turn in one letter to turn into multiple bytes. I'd like the length of the encrypted file to be the same as the unencrypted file. So that means you don't do normal math where numbers just get bigger and bigger. You do modular math on a ring. So here, a clock face is a simple modulus, but here's how you do it. Usually include the 0. So this is modulus 9. There are a total of 9 symbols from 0 to 8. And if you have 9, you just go back to 0. So 8 plus 1 is 0, and plus 1 is 1, and 1 minus 2 is 8. You always go here. So another way to express it is you divide by 9 and keep the remainder. So up to from 0 to 8, you get it doesn't change anything. 9 mod 9 is 0 because it's 1 times 9 plus 0. 10 mod 9 is 1 because it's 1 times 9 plus 1. So this is how modular arithmetic works. You can make numbers as big as you want, but the output will always be between 0 and 9. You can have negative numbers. You can have 0 and go minus 1. You get 8, minus 2, you get 7, and so on. All right, that means you can add numbers. 0 plus 1, mod 9 is 1. 8 plus 3, mod 9. I can take 8 and add 3. I'll get 2. You can also break it up. You can make 15 plus 13 mod 9. That's going to be 28, which is 27 plus 1. So that the remainder is 1. Or you can do these separately, 15 mod 9 and 13 mod 9. This will give you 6 plus 4, which is 10. So you can add and subtract And you can do different modular bases like modulus 4 and modulus 6. It all works the same way. So that's introduction to modular arithmetic. And there's a few challenges for that. And the more interesting twisted one is modular inverses. So now we saw modular arithmetics have addition and subtraction. So let's see if we can do multiplication. Here's the modulus 9. And here we're going to multiply 2 times 9 mod 9. You can do it by just starting from 0, adding 9, and then adding 9 again. You'll end up at 0. Or you can distribute it. 2 mod 9 times 0 mod 9. That's 2 times 0. So multiplication works the way you'd expect. Now, the problem is when you encrypt something, you're going to be multiplying by a key to scramble letters into different letters. When you decrypt it, you'd like to undo that operation. So you'd like to divide. But in modular arithmetic, there is no division. There is no way to divide anything because there's no way to have a half or a third or anything. There is no division. What there is, though, is a multiplicative inverse. So suppose I take all right. So suppose I take 2 times 1. Let me see if I can figure out how I planned this. Okay, here's 2 times 10 mod 9. All right, let's just do 2 times 5 mod 9. 2 times 5 is 10. That's going to be 1. It's going to go 9 to go around once and 1 more. And you can also do it this way. Gets you around in circles. It's 1. This means if you multiply something by 2 and then you multiply it by 5, you've multiplied it by 1. Okay, the 2 and the 5 combined to 1. That means 5 is the multiplicative inverse of 2. So if you multiply something by 2 and you want to undo that operation, you multiply it again by 5. Since there is no division, you can't divide, but what you can do is find the modular inverse and multiply by that to get back the original message. So you can encrypt something by multiplying by 2, and you can decrypt it by multiplying that mess by 5. That's the trick. Now, if you try 6, 6 times 1 is 6, 6 times 2 is 12, that's 3, wrapping around. 6 times 3 is 18, that's 2 9s, so that's 0. And if you keep trying different numbers, you just get 630, 630. So there are certain keys that you could encrypt with that you could not decrypt. They destroy information. There's no inverse for this. If you scramble things with that key on this modulus, you cannot undo that operation. And so here you can try 7. The one way to find the inverse is to just multiply by different numbers. 7 times 1 is 7, 7 times 2 is 5, 7 times 4 is 28, which is 27 plus 1. So this is the multiplicative inverse, the number which gets you 1. So if you encrypt something with 7, you can decrypt it by multiplying it by 4. So here's modulus 4. Just counting up through the numbers. I have 0, 1, 2, 3, and then I'm back to 0. All right. Anyway, so there are some challenges where you do those modular inverses. And that's an interesting thing for students to get used to. They'll need it for some of the cryptography. And another thing they're going to need is XOR. XOR operates on 1 bit. So if the 2 bits are different, the answer is 1. And if the 2 bits are the same, the answer is 0. So this would be your plain text, and this would be your key. And another way to say it is if the key has a 1, you flip the bit. 0 goes to 1, and 1 goes to 0. If the key is 0, you leave the bit unchanged. That's one way to do it. So you can do it in Python with the up arrow command, 0 XOR 0, 0 XOR 1. All right, you can do 2 bits. If you do 2 bits, you just do the bits one at a time. So the left bit here is 0, and the left bit here is 0. So the left bit here is 0. The right bits are 0, so the right bit is 0. Here, the left bits are both 0, so I get 0. The right bits are 0 and 1, so I get 1. You do the bits individually, doesn't matter how many bits there are. And you can do that in Python. If you use 0b before a number, That's a binary number, and you're listing bits here. And you can do 4 bits in Python the same way. All right. And so there are some challenges to solve there. So that's something you might look at. You might want to use this for your students. I'm going to stop this recording.